Hello all. So there was some disturbance in the connection, so I could not continue the last video. So let us continue here. So far we discussed about the transmission line and we have discussed about the behavior of wave. That wave is continuously traveling and hence we does not get the same value what is available at input at the output. So now we'll see few another parameters. So what we are discussing about, say we may have a transmission line and there may be various types of transmission lines. So we may have, say, 2 wire power cable lines. We have to have 2 wire power lines, or we may have overhead power transmission line. These we have discussed about the power line. These are the overhead power lines we used for the movement or the communication of electricity between different cities or towns. Then third one is twisted pair. These are used in the wire telephone. So we have twisted pair. Then fourth one is coaxial cable. These are normally used in the television set cables to connect with the antennas. So we may also have parallel plate transmission lines. So if we consider a parallel plate capacitor, for example, of infinite distance, so one plate can be treated as one conductor and another plate can be considered as another conductor. So if we consider, say, if we can have 2 conductors separated by some insulator here, or normal insulator may be the spatial gap between them, the space. The air medium can also be considered as the insulator between them, and these 2 will be connected with some sort of source with each other. So this may be the 2 wire, or we can also have say microstrip line. Normally nowadays antennas, they use microstrip lines. So I will show you how they look like. Say there may be a strip, a rectangular strip like this, and on this strip there will be mounted say microstrip. So there will be a microstrip on this particular rectangular shape. So this one these 2 mediums will be connected with each other. So say this will be one surface and this will be another medium, and they will be connected with each other with some sort of source. So we may also have microstrip line. So overall these are different type of transmission lines we may have. So but the logic between them is that we have 2 lines and a source, and it may be terminated with some load. Say we'll consider some load here. So this is the load. So if we consider this is our supply voltage V and there is some load L. Let us consider at input side we have point A and A dash. At output side we may consider we have B and B dash. So what we are saying that when our signal is starting at the input, it takes some time to reach at the output. So this is one difference between the normal circuits and the transmission lines. So this time taken by the signal to reach from point A to B is called as transit time. So this transit time is directly related with the length of this particular transmission line. Say if L is the length, so it will be directly related with L, and it will be inversely proportional with the velocity of the wave. Inside wire, the wave is not going to travel with the speed of light. Certainly there will be less speed associated with the wave inside the wire. So if velocity increases, it takes less time to reach the distance. If velocity decreases, it takes more time to reach the distance. So transit time is directly proportional to length L and inversely proportional to the velocity. At input signal, say we are applying some sinusoidal signal. Our sinusoidal signal have the routine meanings of the signal. Say we may have frequency of particular line. Say normally what voltage we get at house, it has normally 50 Hertz frequency. It has low frequency, but we get more power out of these lines. So say we have T, and this time period T is defined as say 1 upon F, inversely proportional to the frequency. So what happens if at point P, so here suppose if we divide this signal into different timestamps, and if we consider that this is the point P and this is point Q somewhere, so when this particular point Q is, say it is appearing at A, suppose at this time the signal which is appearing is Q. So this Q will not appear at B at the same time. There may be some other signal, say probably P may be appearing at B at the same time. So it depends on the frequency and the time period. So we will also try to relate this total time period and this transit time. So here frequency is something which is important. We decide the things. Like say if frequency is going down, if frequency is decreasing, so what will happen? It is inversely proportional to the time period. If frequency is decreasing, time period will increase. So if this time period is increasing, so our signal is going to travel sooner to the destination. So this TR is going to decrease. So if we decrease the frequencies for very low frequencies, this TR may be neglected. So if frequency is increased, so what will happen? It will go opposite. Time period will go down and the TR will go up. So for higher frequencies, we have to consider the transit time. So these are very important for them. So one more thing, we can relate them with lambda. What is lambda? The wavelength. It is given by velocity by frequency. And what is this relation? Now we can say that this is our time period T. So if T is too much greater than say TR, so in this case what can we write? The time period is too much greater than TR, and TR is given by the length between the input and output by length and velocity of the wave. So we can say T is too much greater than L by V. If we write this T in terms of 1 by F, time period is nothing but inversely proportional to frequency. We can write it like this. So from here we can say that, if we replace this term there, we can say velocity by frequency is greater than L, and this thing is nothing but lambda, velocity by frequency. So this lambda will also be too much greater than length. At that time we can neglect the TR. So for higher lambda, if lambda is greater, then TR can also be ignored. This thing we have to remember in this concept. So another next concept we will see about the parameters for the transmission line. So we'll discuss in little detail about these transmission lines. Say we just have two lines, for example. So what may be the parameters related to this line? And these two lines, any two lines carrying current, and they have a considerable distance, they are very lengthy lines. So whenever there is flow of current, say current I is flowing, so we have Ampere's circuited law, we have knowledge of Maxwell's equation, and we know that whenever there is a current carrying conductor, it produces magnetic field around that. So if current is going in this direction, so we may have magnetic field lines like this, a curl rotating around that particular current carrying conductor. So there will be rotating magnetic fields around this particular current carrying conductor. If we have current carrying conductor here, so here also we have the rotation of, say, H, magnetic field intensity. So when there are magnetic field intensities, so these magnetic term will create some kind of virtual inductance. There will be virtual inductance due to this magnetic field. And if we have electric field around that, so between them we will also have electric field intensity between these two conductors. So whenever there is production of magnetic field intensity, there will be production of electric field intensity. Whenever there is production of electric field intensity, there will be production of magnetic field intensity. Electric field intensity travels, say, from positive to negative. If this one is positive and this one is negative, so direction of electric field intensity will be from positive to negative. And this particular electric field between these two conductors will give rise to concept of virtual capacitors. So there will be concept of virtual capacitors and virtual inductors. So you have to keep this thing in your mind, that there is no actual capacitor or actual inductor, but due to the presence of electric and magnetic field, and they are considerable because the length of the lines is very huge. There is not a small circuit. These are meant to have kilometers or meters in length. These are very lengthy lines. So along with these two parameters, we will also have the internal property of material. Like whenever there is a conductor, any material will have its own internal resistance. So there will also be presence of virtual resistance. So we have virtual resistance, we have inductance, we have resistance, inductance. Along with that, we have the capacitors. So capacitance is there. Now what we have to consider, one more parameter will be there. These two lines are not ideal. These are practical lines. Whenever there is a practical circuitry, there will be presence of some leakage current. There may be presence of some leakage current in that. That leakage current will give rise to some kind of conductance. So along with that we will also have conductance present in the circuitry. So for the whole circuit we may have the resistance, inductance, capacitance and conductance. That we will see in the separate diagram. Before that, one more thing we can discuss. Like suppose we are talking about potential difference. Suppose A point is present at the input side and B point is present at the output side. If we consider the lines are ideal, like there is no resistance between the lines, then why don't we get the exact potential difference which is present at input as the same at the output? Even if we consider that internal material resistances are negligible, still there are reactances. The L and C components are not zero. They will exist there because of electric and magnetic field. So that is the reason we will not get the exact potential difference between input and output. So far, suppose if we compare this circuit with the normal routine circuit, say we may have a supply voltage and a small circuitry connected with some component, say normal RLC or something like that, connected with some load. So distance is the less first thing. So whatever is the current available here, same current will go to the load, and if we short the input, immediately output will also be short. There won't be any delay because it is a small circuit. But for larger circuits, for lengthy circuits, we have to consider the transit time and the effect of the reactances. So these two things we have to remember here. So we will have a virtual capacitance, virtual inductance and a resistance and the conductance. So what is the point of our discussion is that any medium which transmits energy through some conducting medium can be considered as transmission line, but these should be two conductors first thing, and there must be production of electric field intensity and magnetic field intensity. And as we know that electric field intensity and magnetic field intensity are perpendicular to each other, and both of them are perpendicular to the direction of propagation. So we have seen in the waves chapter, if our wave is traveling, so we may have E component, and along with that we may have H component, and if they are traveling in Z direction, so E will be perpendicular to H, and all of them will be perpendicular to the direction of propagation. So E may be perpendicular to H and all of them perpendicular to the direction of Z. Same thing will be applicable for the transmission line. So which parameters are important for transmission line? So we will summarize that. So say we may categorize these parameters into three types. So first type is say physical parameters. Say second one is the material parameters, and third one is electrical parameters. In physical parameter there may be length, dimensions, thickness, the diameter of the conductors and what is the spacing between them, and they play important role. If the length increases, resistance will increase and other parameters increase. So physical parameters like length, dimensions, thickness and the spacings, all of them are very important when we talk about lengthy transmission line. And the material, whether we are talking about the conductors or they are insulators, which type of conductors, what is the conductivity of material, what is the permittivity and permeability of the conductor. All of them are very important. Then along with that we have electrical parameters. So we have three parameters, electrical parameters. Right now we have discussed, we may have resistance, inductance, capacitance and the conductance for whole line. And one more thing we have discussed here, that it will not be a lumped value. We will not consider it for the entire line. We have to consider them for smaller portions because these values will be continuously changing. So we will consider the distributed values of R, L, C and G, and they are also called as the primary constants of transmission line. So primary constants of transmission lines are R, L, C and G, and these are not in only ohms or henries. They are in terms of meters. So resistance we have to consider in terms of ohm per meter, and L will consider in terms of say henries per meter. Similarly, all those parameters we have to consider in the terms of meters, and we will consider them for the distributed parameters. So all of them have their routine meanings. I like say resistance. Resistance we will consider as resistance per unit length. So every material has its own finite resistance. Say if we talk about some DC current, in DC current density it is independent of material properties. It depends only on the conductivity. But in AC it also depends upon the skin depth. There is one concept we have studied in third chapter about the skin depth. That also plays important role in skin depth, that we will discuss after some time again what is the skin depth. But we have to consider this thing also. At high frequency only a small skin contains the current. What is this skin effect? For example, suppose this is some kind of medium and there is fall of some wave in terms of electric field or magnetic field on this, or suppose there is current flowing across this particular medium. So normally these charges will flow on the surface, but how much deep they can penetrate inside the material, that depth is given by the skin depth. At high frequencies only small skin contains current. For example, at depth of 5 skin depth, the current density is less than 0.7% of the current density at surface. So whatever current is flowing on the surface is the maximum current, say 99 point something. So say 99.3% current flows on the surface, and at very small portion beneath the skin we get around 0.3% of current. So maximum current it flows on the surface. So normally it is referred as surface current density only. That current flows on the surface. So this laptop is off, so no problem, we'll discuss it on paper only. So now let us discuss about the equations of voltage and current. So they are referred as transmission line equations. Transmission lines equations. So one more time we will discuss what is a transmission line. We may have lengthy transmission lines, and what we do, we divide them into distributed elements so that we can calculate the values. Say this is delta x or dx, small differential portion. In the small differential portion, if we zoom it, so what will be the parameters present there? We'll have one, say L, R, C and G. So for the differential length, there will be, say, L plus some delta x. Here we may have R plus some delta x. So this will be C plus delta x. This will be G plus delta x. So similar setup will be present in each of the distributed element. One more time I repeat, these are the virtual inductance and capacitances created due to magnetic and electric field. We are not connecting direct inductors or capacitors in the line. These are simple two lines or two wires. So how it will look in the whole? So in whole we may have L, R, L, R, L, R, and so on. And similarly we may have C, G, C, G, and so on. So if this is L, R, C, then again we'll have, say, L, R, C, G, like this. So capacitance, conductance, inductance, resistance. So for different distances, say per meter, we have to consider. So what will be the expressions for this? First we know the Ohm's law, the simple Ohm's law. So we know we have V is equal to I R. So here resistance is because of these two terms here, L and R in series. So what we will get here? Say if we want to calculate the delta V here. So if at input side we are giving some voltage V, there will be some change in the voltage at the end of one element. We are just zooming the small part and we are considering that part. So in that, say, there will be V plus delta V. Similarly, if current I is entering here, so here we will get I plus some change in current delta I. So if we have to consider this delta V, and this delta V will be part of R delta X plus J omega L delta X into I. So this is our expression 1. Now this delta V will have smaller value than the voltage. Once we apply the voltage, there may be some loss, but we are not going to gain any voltage. So this value will be negative. Similarly, for this change in the current, so change in current will have delta I is equal to minus of G delta X plus J omega C delta X into V. Say this is equation 2. So these are the two equations. They are mutual relations. They are giving relation between I and V and so on. So they ultimately satisfy the Ohm's laws, like say V is equal to I into R. Here R is because of total resistance and the inductive element. So and negative indicates that there is less current or less voltage at the output of one lumped element. We are talking about only one lumped element, and we are talking about only one element, not the entire element. So we have these two expressions. So say taking delta X common, so what we will get, delta V is equal to, so delta X we are taking common here, say delta X, and then R plus j omega L into I, and similarly delta I will be minus delta x plus g plus j omega c into v. So we will change this, we will shift this delta x to the LHS. So what we will get, say delta v by delta x. Same thing we can write it as, say, dv by dx, differential element, or dv by dx is equal to, we will get minus of r plus j omega L into I. Say this is expression number 3. Similarly, we'll get for delta I by delta x. So we're shifting this to LHS, or we can write it as di by dx. It can be written as minus of g plus j omega c into v. So this is expression number 4. So these are the two expressions. So now we will take the derivative of expression 3 and 4. Let us write them again. What we got? Say we have dv by dx is equal to minus of r plus j omega L into I, and we have di by dx is equal to minus of, say, g plus j omega c into v. These are our expression 3 and expression 4. So taking derivative of, say, equation 3, what we will get? We will get d square v over dx square is equal to minus r plus j omega L into di by dx. So we already have di by dx here. Keeping this value here of di by dx, so what we will get? d square v by dx square is equal to minus r plus j omega L. Minus minus will become plus, so here we will get g plus j omega c into I. So this is expression 5. This whole term, here we will get the V voltage. This whole term is given by gamma square, where gamma is propagation constant. This is propagation constant. So this whole term we can reduce to d square v over dx square equal to gamma square v. So this is expression 6. Now same steps we can apply for di by dx. We can take derivative, double derivative we will take, and you can write this term as d square I by dx square is equal to gamma square I. This will be, say, expression 7, where gamma is propagation constant. In third chapter we have discussed about it. One more time we will revise it in some time. So here these are two transmission line equations. What we are talking about, the transmission line equations. These are the two transmission line equations. So what we have to do now, we are talking about some transmission line, and in this transmission line our electromagnetic wave is traveling across this line. It is creating a virtual pair of L, C, R and G, and we are getting all those expression in terms of, say, voltage and current. So these things we have to relate with the routine electric field terms. We have electric field intensity. We have 4 terms. Previously we have discussed about E, H, D and B. These are the field terms. So we have to relate them with the electric field intensity. If we remember, we'll try to discuss the relation between V and E. V is circuit component voltage and E is field component electric field intensity. First relation, what we have derived earlier, is that V is equal to integral of E bar dot dl bar. Those who remember this, okay, fine. If not, we have the definition and the unit of electric field intensity. What is unit of electric field intensity? The unit of electric field intensity is volts per meter. So basically it is voltage given per meter. Here you can see, say dV by dx term, voltage per some distance. Its unit of electric field intensity is nothing but volts per meter, volts per some distance. They are interrelated with each other. So what we can say from here? So we can say that voltage, if we shift this term towards left, voltage divided by differential length, that is electric field intensity. That is the definition of electric field intensity, voltage per meter. This thing we have to remember. Now further we will correlate them, but before that we have to remember, we have to recall few expression from the wave, and then we will relate with the voltages. So what we have to remember? So what to remember here? We will revise few terms which are required in our discussions in this chapter. First we have the Ohm's law, V is equal to IR, and then we have to remember the current density J is given by sigma E, where sigma is the conductivity and E is the electric field intensity. For voltage we should remember it is integral of E bar dot dl bar. We have to remember unit of electric field intensity is volts per meter, and we know that J is equal to, say, di by ds, hence I is equal to integral of J bar dot ds bar, or simply we can have a relation between I and J is I is equal to J S. So at the end of transmission line equation we came across some gamma term. Gamma is propagation constant. Now propagation constant, what we are propagating? We are propagating a wave. That means we are sending a wave from one place to another place. If it is a transmission line, in transmission line at one end we are sending the wave and we are going to receive at another end. So wave is particularly combination of two things. In a wave, first thing we have a phase. Second thing we have some kind of, say, we have phase and we have some kind of amplitude for the wave. This wave consists of some frequency. So phase and amplitude are the two parameters of a wave, and this complete wave travels along with its energy. That means this wave propagates along with the phase and amplitude. So this particular gamma, propagation of wave, is a complex term. It is given by alpha plus j beta. What is this alpha? This alpha is nothing but the concept related to amplitude, which is attenuation, and beta is related with the phase. So beta is phase and alpha is attenuation. So why attenuation is related with amplitude? So for that we had seen the uniform plane wave and non-uniform plane wave. Whenever we have a wave and which is practical wave, if it starts with particular amplitude with some energy, after distance it keeps on decreasing. it keeps on losing its energy. It has some exponential movement. So exponential equation, in the equation exponential part is very much essential when we talk about a wave when it is traveling. So whenever there is amplitude, it is directly related with attenuation. There is attenuation in the wave and there is some phase of the wave. So this propagation constant is combination of alpha plus j beta. This is a, and say we have some kind of amplitude and the wavelength for this particular wave. So now if we consider that our wave is traveling in z direction, so the direction of propagation is z, and this wave is exponential in nature, and say this is the front view where only electric field intensity component is visible. So say then we can write the exponential expression for this electric field intensity for gamma is equal to alpha plus j beta. So the general solution for this propagation of wave which is exponential in nature and the wave which is going in z direction, so what we can write it, it will have two parts. Say this is the wave, the component of E, say E is vibrating in x direction for example, and the movement is in z direction. At distance 0, we will have two parts of this wave. First will be the positive part, which will be the forward wave or the incident wave. It will be given by say e to the power minus alpha z into e to the power minus j beta z, plus there will be a backward wave that will be negative, that is at distance 0 minus, so if it is positive this will be negative and these are minus, so here we will get exponential term of alpha and beta as positive, so it will be alpha z and e to the power j beta z. Now what is this thing? Say we have a wave, say which is traveling towards z direction. So this wave is say traveling towards z direction. So we will have one component of field which is forward. Say there is a forward wave, and if it is reflecting back, we may have a backward wave. The concept we have discussed in the beginning of this video, that is standing wave ratio. Normally we consider the equation for forward wave only, but we should also know how to write the combined wave. So the whole wave, so this is the wave, and this part is for forward wave and the remaining part is for the backward wave. So complete wave is combination of forward wave and backward wave if backward wave exists. And what are their terms? We have alpha and beta. So we'll write down only for the forward wave the expression. So for forward wave only, if we don't consider the SWR, so for forward wave, say the wave traveling in z direction is a positive wave, e to the power minus alpha z into e to the power minus j beta z. So what is this alpha j beta z? This is nothing but the gamma concept, alpha plus j beta. We can write it in terms of gamma also. Say this will become, this is nothing but e to the power minus alpha, sorry, this is e naught plus e to the power minus alpha plus j beta, which is traveling in z direction. So this wave, what is the meaning of this? So e to the power gamma z, this is e to the power gamma z, the propagation of exponential wave in z direction. The simple meaning of this wave is, we have electric field intensity component which is exponential in nature, which is continuously reducing and propagating in z direction, and propagation constant is alpha plus j beta. Now we can further have the general solution in time domain. So how to write this same expression in time domain, that we will see. Say a general solution of this wave in time domain. So again we may consider back the forward and backward wave. So here we have to consider the space and time component also. So wave is moving in z direction, and here we are considering the time. So this will be equal to the forward plus for the forward wave, then e to the power minus z. This will be solved as cos of omega t minus beta z. This will be for the forward wave. For reverse wave, we will have the same expression with minus sign, and here we will get the positive sign alpha z cos of omega t plus beta z. So this is for the reverse or backward, and this one is for the forward wave. So we can write, so for forward wave only this wave we can consider, if it is only forward wave. We'll discuss what is the physical instant for forward wave. Say let us consider the forward wave. Forward wave we have seen. Now how this timestamps changes. Now same thing we can write for the voltage. What is the relation between E and V? For our transmission lines we are talking in terms of voltage, and here voltage, this E is nothing but volts per meter. So this expression we can write for the voltage. Say voltage for z direction, it will be equal to the forward voltage e to the power minus gamma z, it is going in the z direction, plus for the backward electric field voltage, that is e to the power gamma z, and its solution in the same form we can write for the forward wave. So for V, if we take the time domain, V z of t, it will become V plus e to the power minus alpha z. We can split this gamma into alpha and beta to the power minus alpha z cos omega t minus beta z. So this one is for forward. Let us see physically for this particular omega t minus bz for forward wave, and for different timestamps we can see what is this expression. So we will take some real part of this expression. What we will get, say for forward wave, only for forward wave voltage V plus e to the power minus alpha z e to the power minus j omega t minus beta z, and for alpha equal to 0 there is no attenuation, then we can say that V plus is real without any attenuation or cutting of the wave. So this one, the real part, we can write V plus e to the power j omega t minus beta z. However, whatever the expression is, either this is the expression or this is the expression or the expression for electric field intensity, we can see all of them are same. This expression is same as this expression. For forward wave in time domain, it is with the cos of omega t minus beta z. So what does that really mean? Say we have a movement forward wave, this suppose time is, we are changing the time. So this particular flow is for the forward wave omega t minus beta z, the forward wave. So for forward wave, say we have something like this. So A is shifting from here to here to here. So this line, this is forward wave omega t minus beta z. If we consider the backward wave, so we will have the opposite flow. So we may have some wave, the same wave at different time is stamp. Suppose A is there, going backward here, then going backward here, and this flow is like this. But at the time, this will be omega t plus beta z. So this particular thing will be omega t plus beta z. So here we have seen the relation between electric field intensity and voltage, and we have derived the various equations. In next video we will see the other parameters related to transmission lines.